Sometimes the hardest part of solving a math problem isn't getting to the answer, it's figuring out how to get back to the beginning. Today, we're diving into what you might call a master recipe for reversing one of the trickiest shortcuts in all of mathematics. So, how in the world do computers crack equations that seem, well, impossible? Well, what if I told you it's not always about finding one single perfect method? Sometimes it's about finding a better recipe, a flexible framework that you can adapt to pretty much any problem you throw at it. All right, let's start with what I like to call the transformation trap. We're going to look at a super powerful mathematical shortcut that, it turns out, has a hidden and very, very difficult challenge baked right into it.
Okay, so in science and engineering, you are constantly running into these incredibly messy calculus problems, right? Things like differential equations. The Laplace transform is a total game changer. It's this genius shortcut that takes all that complicated calculus and just turns it into simple algebra. You solve the algebra, which is way easier, and boom, you get a transformed answer.
But, and this is a big but, here's the trap. That neat little algebraic answer, it's not your final answer. It kind of exists in a different mathematical world. To get the real-world solution you actually need, you have to reverse the whole process. And as it turns out, going backward is monumentally harder than going forward.
So, how do we escape this trap? Well, let's take a look at the official integral escape route, which, as you're about to see, is often a lot more theoretical than it is practical. This whole reverse process has a name. It's the inverse Laplace transform, and it's the absolute final, crucial step. It's all about taking that clean algebraic solution and turning it back into a function that actually describes the real-world thing you were studying in the first place.
Now, if you crack open a textbook, the official by-the-book answer for this is something called the Bromwich integral. It's this elegant-looking equation and that promises to give you the exact inverse. Sounds great, right?
Well, what does that elegant integral actually look like? It looks like this. It's a path integral that has to snake its way through the complex number plane. And this visual right here shows you exactly why the elegant solution is a total nightmare for computers. Actually calculating this path is incredibly intensive, often impractical, which is why for decades, researchers have been desperately searching for a better numerical way to do it.
And that search for a better way didn't lead to just another new algorithm. Nope, it led to something much bigger, a unifying framework. And this is the absolute breakthrough idea from a paper by Joseph Abadi and Ward Witt. They basically said, hey, let's change our focus here. Instead of trying to create one more specific method, they designed a flexible system, a framework that could basically hold all these different methods under one roof. They changed the entire perspective on the problem. And this equation right here, this is their master recipe. It's the core idea. You get an approximation of your function by taking a bunch of different values of your transformed function, multiplying them by some special numbers, and then adding them all up. The magic isn't in one fixed set of instructions, it's in how you choose and combine those ingredients. So think of it like this. The weights and the nodes are the pre-calculated secret ingredients. The beautiful thing is, they don't depend on your specific problem at all. You just plug them into the recipe with your transformed function, and out pops a highly accurate numerical answer. It makes the whole process incredibly efficient. Now, to show just how powerful their framework was, Abate and Witt showed how 3 really well-known algorithms were actually just different flavors of their master recipe. And here are the 3 main flavors. You've got Ganver-Steffist, which is really cool because it manages to do everything using only real numbers. Then you have Euler and Talbot, which both use complex numbers. But check out that efficiency column on the right. The Euler and Talbot methods are about 50% more efficient. You get way more bang for your computational buck. But this is where the framework goes from just being clever to being truly groundbreaking. Because all of these algorithms share the same basic structure, you can start combining them in really surprising ways. This is the power of mixing. See, a lot of real-world problems aren't just one-dimensional. They're multidimensional. With this framework, solving a 2D problem is suddenly super straightforward. You just apply the recipe twice, once for the inner dimension, and then you just do it again for the outer dimension. And here's the kicker. Because you can use any of those 3 algorithms for each step, you don't just have 3 tools anymore. No way. You instantly create 9 distinct, powerful, 2-dimensional algorithms. And this leads to the most important takeaway of the whole thing. The paper shows that it's often actually better to mix and match. A hybrid algorithm, say using Talbot for the first step and Gabor-Stufist for the second, can be way more efficient than using Talbot for both. This proves the value of the framework. What you get is a flexible toolkit, not just one rigid answer. Now, this might seem like a niche little story from mathematical history, but trust me, the story does not end there. This incredible idea of a flexible framework is now right at the heart of a brand new frontier: artificial intelligence. That's right, the core concepts that Abate and Witt developed all those years ago are so fundamental that they're now being used to build new kinds of neural networks, AI designed to solve the very same differential equations the Laplace transform was originally created for. For a while, the go-to AI model for this was the Fourier neural operator. It's powerful, but it's got a weakness. It's best for signals that repeat, like a smooth, predictable wave. But now there's a new model, the Laplace neural operator, and it's built on the very ideas we've been talking about. It excels exactly where the other one struggles. It's perfect for handling the messy, start-and-stop, unpredictable signals that we see all the time in the real world. And this just leaves us with a final thought. This whole journey from a complex integral to a flexible AI tool, it just shows the immense power of changing your approach. It really makes you wonder, doesn't it? What other great challenges are out there, waiting, not for one perfect answer, but for a master recipe that lets us create thousands of them?